In this video, we're going to explore the basicity of amines again, but this time as it pertains to answering a Fall 19 Test 3 question in the short answer section of the exam. We have to progressively protonate this species one time with this acid and then another time from the product with this acid. The question is, which of these nitrogens is the best base? Let's look at all of them individually in this order and see what we come up with. If we wanted to protonate the top nitrogen, this would be the second worst choice. This ammonium ion you created here no longer has a lone pair as did this nitrogen up here. So a lot of resonance with the aromatic ring is lost. So that would be our second worst position for the proton. Moving to the pyridine nitrogen. It's not a great place to put a hydrogen either. You don't lose resonance with benzene, but you do have an sp2 hybridized cation. And that is not a good situation because sp2 is 33% S, which brings the plus closer to the nucleus. Moving over to this nitrogen. This is not a bad position to put a proton, even though, as we just discussed, both of these nitrogens are sp2. The imidazole nitrogen in this area here can resonate with two equal resonance forms with the other nitrogen. So that situation makes an imidazole an unusually attractive base because of the stability of this resonating sp2 cation. And the top one, top right, is the absolute worst spot to put a proton because this imidazole ring is no longer aromatic at all. You've lost aromaticity. Never use a lone pair that was being used for aromaticity to pick up a proton. With all this in mind, I think we decided that this would be the best product here. And we're going to put a pKa on it eventually. Might as well now. In a imidazolium ion, you should learn, this is a new pKa that you should learn, has a pKa of 7. And the acid here is carbonic acid. It does not have a pKa of 7. It has a pKa of 6. This gives us a pKeq for this equilibrium of 6 minus 7. Let's show that work. pKeq for this equilibrium, 6 minus 7, negative 1, gives a KEq of 10 to the negative 1, which is 10, which means we should circle the arrow pointing towards the products since we have a ratio of 10 of these for 1 of these. Circling the arrow going forwards. All that remains is to calculate pKb for each base. If you don't have an acid, then you have a base. So, what is the pKb of this base? It is 14 minus the pKa of this base's conjugate acid, which is 7. 14 minus 7 is 7. pKb 7 here. Similarly, pKb for this. 14 minus 6 is 8. And I believe that covers all parts of the question. As for drawing MTSOH, we have to realize that M stands for meta, T stands for toluene, S stands for sulfonic, OH is the acid. Toluene is methylbenzene. In the meta position, we have a sulfonic acid. And that is metatoluene sulfonic acid, a strong acid. pKa is negative 5 approximately for that one. -5. Now the question is, where are we going to park the next H on this species here? Which of these three positions is going to be used to pick up the proton? Well, we already discussed it. The worst situation was to put it here. This was the best. Sorry about that. Worst, terrible, lesser of evils, that's the spot we're going to put it. So a little reviews in order to figure out the pKa of this one. Our aliphatic amines, those are our normal alkylamines that we learned about back in the day. Because an ammonium ion has a pK of 10, the pKb is 4 for those. Imidazole, as we saw above, 14 minus 7 is 7. The trend is the numbers are getting bigger because aliphatic amines are the strongest amines as bases, and the worst will be aniline. Pyridine, just keep going down by 1 for your pKa's. Pyridinium, roughly pKa 6, therefore pyridine, pKb, roughly 8. Anilinium, pKa, roughly 5. Gives a pKb for aniline. 14 minus 5 is 9. And we're looking at a pyridinium species right here. That'll give us a pKa of roughly 6. Right in there. Keep in mind, in part 1 this was an acid, but in part 2 it's acting like a base. So the pKb of this is 14 minus the pKa of its conjugate here. 14 minus 6, 8. pKb of the metatoluene sulfonate ion is 14 minus the pKa of metatoluene sulfonic acid, -5. That's some interesting math there. 14 minus -5 is 19. KEQ for this. KEQ. -5 minus 6. This acid here minus this acid here, -11. KEQ 10 to the positive 11. And the only thing here is to circle the arrow. Definitely going away from a weaker acid towards a more stable acid means we should circle this arrow right here. And that concludes that part of the equilibrium. Next up, we're supposed to draw the Lewis structure for ACOH, AC short form for acetyl, CH3 bonded to carbonyl. Don't forget, Lewis structure, you have to show every bond, every lone pair. So here we have acetic acid. The pKa of acetic acid is 5, as most carboxylic acids are. The pKa of aliphatic amines, as we summarize down here, is 10, not 6. So the pKa of the reaction going from 10 towards 5 is 10 minus 5 is equal to 5. KEQ is 10 to the negative 5, means we should circle the reverse arrow. We have 100,000 times more reactants than products. The question is, what goes into our box? Which of the aliphatic ammonium ions is a little more acidic? And this was discussed previously, that a secondary ammonium ion right here is the most stable of the ammonium species because it has a good combination of hyperconjugation caused by 2 carbons attached, and it has good hydrogen bonding with water with 2 hydrogens attached. Tertiary ammonium ion has triple hyperconjugation, which is a little better, but it loses out in a fairly large way with only having 1 hydrogen to hydrogen bond with water. So this species is more stable. I don't want to take its H off before I take the H off of a species that's less stable. So that's where I'm going to remove the H. So this is the base for part 3. It has a pKb of 14 minus 10, which is 4. And the base acetate, I'm going to have to squeeze it in somehow. Acetate, the pKb is 14 minus acetic acid's pKa, which is 5. Snuck it in here. 14 minus 5 is 9. Now starting all over again for part 4, we have another ammonium ion. pKa is still close to 10. And the acid in the products is ethanol. The two smallest alcohols, ethanol and methanol, have pKa's of 16. Most alcohols between 17 and 18. The conjugate base of ethanol is ethoxide, and it has a pKb of 14 minus 16 is negative 2. And the conjugate base of this acid will be this species here with a pKb of 14 minus 10 again. pKeq would be the acid in the beginning, which is 10 minus the 16 at the end. It's negative 6. KEq, 10 to the negative 6, which means the products are definitely favored in this equilibrium here. And I hope we finished all the parts. I'll verify that and come back. Looks like we got all the parts. I'm just going to do a quick verification going backwards. This is a base. The best base is the secondary aliphatic amine. And it will create the secondary aliphatic ammonium. And then the next best base is the tertiary amine. And it will create the tertiary aliphatic ammonium ion. And I believe that's the end of this video, and I hope you found this useful towards understanding the basicity of amines, and I look forward to our next video.